Hi, I'm Zoya.
I'm Brandon.
I am you.
I'm Michael.
And we're doing using machine learning to predict autism in toddlers. So before we get into the research process, here's some background information. Autism spectrum disorder is a developmental disorder often identified by combination of social interaction and communication. It's usually distinguished from observable symptoms like communication, speech, and general behavior, which makes it really difficult to diagnose because you have to make sure you're physically observing it. This causes a lot of concerns to arise to parents and families, one of them being the cost. However, early screening can reduce this, and we aim to adjust that by improving the diagnosis pipeline of ASD by training an ASD dataset with a machine learning model, which led to a more personalized and early stage treatment. About 1% of the entire world population suffers from ASD, and there's no known cause or cure for it. However, there are some medications to alleviate symptoms. We expanded on previous research done by Fatty A. Tabata. We first augmented the data using light GBM parameter optimization, which allowed for us to create a larger data set in order to yield higher accuracy. Specifically, we used neural networks and random forests in order to improve model accuracy. This resulted in not only a highly accurate classifier, but we were able to use feature selection in order to identify which factors were the most significant in contributing to early stage autism.
So as you see on the next slide, in order to find out which characteristics most correlate with autism, we obtained a data set from UC Irvine. The data set included 18 variables. 8 of these variables are the possible characteristics that could correlate with autism, and 10 of these are questions. Now with these 10 questions, there are 2 groups of answers. Answers that basically reflect that your child does have autism, and answers that basically reflect that your child does not have autism. And if you answer in a way that reflects that your child does have autism, you are given 1 point. And if you answer one of these 10 questions in a way that reflects that your child does not have autism, you are given 0 points. And basically, once you add up all these point values of these 10 questions, you have your Q-Chat-10 score. And if your Q-Chat-10 score is 3 or above, it is likely that your child has autism. So as we see with the data, with the actual data set on the next slide, the first question is, does your child look at you when you call his or her name? And basically, if you're confused, you just have to. I'll guide you on an example with this question. So it is. If you answer this question with no or not really, that answer reflects that your child does have autism, thus you are given 1 point. If you answer yes or yeah they do, that answer reflects that your child probably does not have autism, so you are given 0 points. And this continues on for the 10 questions, and if you answer in a way that reflects that your child does have autism for at least 3 of these questions, we basically come up with the conclusion that it is likely that your child has autism. The other 8 variables are on the next slide, and as you see, these variables include sex, ethnicity, and jaundice, and these variables are the actual variables that we are seeing whether it correlates with autism or not. And out of these 18 variables, 16 of them were analyzed using random forest models or in neural networks, and we excluded the Q-Chat-10 score and who completed the test variables because they are not exactly relevant. And this next question, if you're in the audience, you don't have to answer this. This is purely rhetorical, but honestly, which characteristics in the data set do you believe most correlate with autism? Because the results will actually surprise you.
Okay, so I'll discuss the methods and implementations that we utilized on our data set. First, we split our data and used 20% of it in order to create a baseline data set. Then we used an algorithm called an XGBoost classifier. With this algorithm, we were able to make our baseline data fit a model with 97.04% accuracy. After our baseline data was acquired, we designed a 3-level perception model of the data. This can be seen on the left. Basically, each of these layers does something different to help further classify the patient data. Although after the model was trained and tested, we concluded that no optimization of the neural network was necessary because the network outperformed the baseline and perfectly classified all patients in the test set. Here is an evaluation of our model. Each trained model was used to predict how every patient in the dataset would be classified. So the predictions were then compared to the ground truth classes of all patients using these 4 metrics: the recall score, which is the ability of the model to identify positive patients as positive, and the precision score, which is the ability of the model to not classify a negative patient as positive. Then it's the F1 score, which is the weighted average of the precision and recall score. And lastly, the accuracy score, which is the ratio of the number of correct classifications to the number of total classifications performed. So another type of model that we used was a random forest model. This model was designed to use gradient boosting, deviant loss function, to have a learning rate of 0.01 and have an estimated count of 1,000. This model was evaluated using the 4 metrics previously said on the last slide. And due to a slight model inaccuracy, we performed a grid search to return the best classifier.
The next step in our research was feature selection, which consisted of developing a hyperparameter optimization function, using this function to develop and optimize the random forest model, and then extracting the feature importance scores calculated by this model function. We then used light GBM parameter optimization to calculate optimal values for all hyperparameters for random for Here we show our results. In figure A, we show the performance of baseline XGBoost model, the mean accuracy of 97% and the standard deviation of 1.78%. And in figure B, we show the evaluation metric performances of each model on testing set patients. So you can see the pre-optimization random forest classifier and post-optimization random forest classifier, and the increasing percent to 100%. Here we show the feature and the importance score, the importance scores of the 10 most important features calculated. So for each feature, you had the corresponding importance score, and they're arranged in order from least importance to greater. In this figure, this is the bar graph representation of the calculated importance scores of each feature included in training and testing models. So in this study, novel research was performed regarding the detection of autism in toddlers, and some notable takeaways are that standard neural network and optimized random forest models are reliable in clinical decision justification, and we identified the least ASD indicative questions, and sex and familiar autism have zero impact on determining autism. Some future work which could be done are clinical testing can be performed using machine learning models to further validate its real-world efficacy in determining autism in toddlers. In this way, we'd be increasing the size of the data set and using other machine learning models and figuring out why certain questions are more indicative of autism in toddlers than others are. Thank you. Does anybody have any questions?